Hello dear students, welcome back to the series of lectures series of lectures on major theory with course code MMTC 202. So today in this lecture we'll prove a theorem that we called the order continuity integrals of the integrals of step functions. Let me state this theorem here. This theorem is called the order continuity of the integral. Order continuity of the integral of step functions. Okay, let the statement is let phi and base frequency of step functions. Let phi and base frequency of step function, let phi n be a sequence of step function is phi and base frequency of step function is now if this sequence decreases to 0 almost everywhere, if phi n decrease to 0 almost, that means this sequence is a decreasing sequence and its limit is equal to 0. Sequence decreases to 0 almost everywhere, then integral of phi n will decrease to 0. And in particular it shows that in particular if phi is a step function, if phi is a step function such that this phi n increases to and phi n increases to 5, then it's almost everywhere. Then integral of phi n increases to integral of phi, then integral of phi n increases to integral of phi. That is the statement of the theorem. Given a sequence of step functions which decrease to 0 almost everywhere, then integral of phi n will also decrease to 0. And in particular, if phi is a step function and phi n increases to this step function phi, then integral of phi n will increase to the function to this integral of phi. First we verify that this we can assume that this phi n will decrease to 0 for each x and x. We can assume this. So first let's verify that. So for this we define sets. Okay, we define sets where this where this convergence does not hold. Actually, we try to find out that set. So let's since assume phi n decrease to 0 almost everywhere, and let's define this set that means it's monotonic decreasing sequence almost everywhere. So let's define this set a n for each n. Define this set x where this is increasing, it's not decreasing. This where this phi n plus 1 is greater than phi n. It's given that phi n plus 1 is less than or equal to phi n almost everywhere. Now we define a set a n where this reverse inequality holds, and define the set a naught where convergence does not hold. Define the set A naught which is equal to x belongs to x, such that phi n does not, the limit of phi n is not equal to the zero function. Then you can see this, the measure of an is 0 because this phi n plus 1 is less or equal to phi n almost everywhere. Therefore, the set where this this inequality less or equal to inequality does not hold must has measure 0. So that's the set an. So that means measure of an must be equal to 0 because the inequality is reversed. And since also this phi n, the limit of phi n is equal to 0 almost everywhere, therefore the set where this limit is not equal to 0 must be a null set. So that means measure of a naught is equal to 0. So then mu star of an is equal to 0 for all n equal to 0, 1, 2, so on and so forth. Now let's define this set A, which is the union of these sets. Let A is equal to union A and n runs from 1 to infinity. These areas need not be disjoint, but we can apply the sigma subadditive property of mu star by sigma subadditive property of mu star. We have mu star of A, which is equal to the mu star of union. So that's less or equal to by subadditive property summation n runs from 1 to infinity mu star of an. So this union varies from 0 to infinity, not from 1 to infinity, okay? 0 to infinity. 0 to infinity. Now since measure of each an is 0, so this must be equal to 0. So that implies A is a null set. Mu star of A is equal to 0. Mu star of A is equal to 0. Okay. So then you can see this. Then also we have the following. Also this phi n decreased to 0. It decreased to 0 for all x belongs to a complement. Okay, and this is decreasing less or equal to phi n for all x belongs to a complement, because on the sets on a n complements the on a not complement, because this x belongs to a complement means it belongs to a not complement also. So whenever x belongs to a not complement, this limit of phi n is equal to 0. And it also x belongs to a complement means that x belongs to each a n complement, and whenever x belongs to each a n complement, then phi n plus 1 will be less or equal to phi n, because on a n the reverse inequality holds. Okay, so that's why this phi n, it will decrease to 0, and phi n plus 1 less or equal to phi, it is decreasing. So you can say limit is 0 for each x belongs to a complement. For each x belongs to a complement. Now let's define this, define new step function. Define psi n is equal to phi an into characteristic function of a complement. Then psi n is equal to phi n on a complement, and on the rest of set psi n is equal to 0. Then because on a complement this is equal to 1, so this will be equal to psi n equal to phi n. Then psi n is equal to phi n on a complement, and psi n is equal to 0 and not equal to phi n on a, but measure of a is equal to 0, so therefore I can say this psi n is equal to phi n almost everywhere, and also psi n decreases to 0 on x, on whole x, because on a complement phi n decreases to 0. Here you can see on a complement phi n decreases to 0. Okay, you can see it here. And on a n complement phi n is equal to psi n, therefore on a complement psi n will decrease to 0. But on the rest of the set, this psi n is equal to 0. On the rest of the set, psi n equal to 0. So that means I can say psi n decreases to 0 for on whole x. On whole x. So psi n is a decreasing sequence on whole x, and the limit of psi n is equal to 0 on whole space x. On whole space x. So this also means that also this because psi n is equal to phi n almost everywhere, integral of psi n is equal to integral of phi n. So therefore we can replace this phi n by psi n if necessary, because it will not harm as the integrals are also equal, because we need to show that integral of phi n will decrease to 0, but integral of phi n is same as integral of psi n. So if we will show that integral of psi n will decrease to 0, then it will give integral of phi n also decrease to 0. So if we replace phi n by psi n, it will harm nothing. So it means that we can replace it if necessary. But for this psi n, it decreases to 0 on whole x. So therefore we can replace phi n by psi n if necessary, and hence we can assume that, this psi n, our given step function, this phi n, the given sequence, will decrease to 0, sin of x decrease to 0 for all x in x, because sin decrease to 0 for all x in x. So we can replace this phi n by psi n if necessary. If it already holds, then we don't need to replace it. But if it does not hold already, then we can replace this phi n by psi n, and we can say this phi n of x decrease to 0 for all x in x now. Okay, so now we come to the proof of the theorem. Now let epsilon be any positive number. Now let epsilon be any positive number, and put this m, which is the maximum, which always exists, which is maximum of it's the maximum of the set. This m is equal to maximum of it's the maximum of the set. It is this maximum of this phi 1x. It exists because phi 1x is a bounded function. It has only finitely many values, so we can find its maximum value. Okay, and this x is in x. And let's define b, and b is x belongs to x such that phi 1 of x, okay, is positive. So clearly this measure of b is finite. It's a finite because phi 1 of x is a function. It has the standard representation such that the measure of the each set in this representation is finite. So that means measure of b must be a finite, where it has only positive values. The measure of that set, it's a union of the sets actually, where it union of those sets where it has positive values. Okay, suppose it has three positive values, say a1, a2, a3, then it will be the union, then b will be the union of these a1 capital a1 capital a1 a2 capital a3. But the measure of those sets is finite, as phi1 is a step function, so that means measure of b is finite. Then measure of b is finite. Then measure of b must be finite. So this is not difficult. This is very simple actually, because b is the union of the sets where it will take the positive values. Okay, and measure of each set is finite, so that means measure of b will also be finite. Is also be finite. It's a finite number. Now for each and define for each and let's define en, which is equal to the set x belongs to x, such that phi n of x greater or equal to epsilon, phi n x greater or equal to epsilon. Say e1x means phi 1 of x greater or equal to epsilon, e2x means phi 2x greater or equal to epsilon. Then then this set, then measure of the set e1 is obviously finite. This is again by definition of step function is finite, because it's the union of the finite sets. Union of the sets of finite measure, and it's obviously the finite union, because the phi 1 it's a step function, so it has only finitely many values. So that means there are only finite values for which phi 1 of x is greater or equal to epsilon. Okay, so mu star of e1 is finite, and also each en is measurable because phi n is measurable. Also each en is measurable as phi n is measurable, as phi n is measurable, as phi n is a measurable function, as phi n is measurable function, you can write here. Therefore the set en must be measurable. It is the definition of measurable function actually. Now we verified that now we verified that this en, its decreasing sequence en plus 1 is subset of en, and the intersection of en runs from 1 to infinity is equal to the phi set. So that means actually I need to show that this en it decreases to phi actually. So decrease to phi means this, I need to show that it's a decreasing sequence and the intersection is the phi set, which is the null set. Okay, so this en plus 1 is subset of en. Let's take this x, let x belongs to en plus 1. We show that it is in en also. So by en plus 1 we mean that where is en? The set en is this. This means that phi n plus 1 x is greater or equal to epsilon by definition of en. So it implies that phi n plus 1 x is greater or equal to epsilon, but phi n is greater or equal to phi n plus 1 because phi n is a decreasing sequence. Phi n is greater or equal to phi n plus 1 because phi n is decreasing, and phi n plus 1 is greater or equal to epsilon for this x, for this particular x. Phi n x is greater or equal to phi n plus 1. This is true for each x, but for this particular x, this is greater or equal to epsilon. So which means that phi n x is greater or equal to, this is greater or equal to epsilon, but this again means by definition of en, x belongs to en. X belongs to en. So thus en plus 1, thus en plus 1 is subset of en. Now assume on contrary that this intersection is not equal to phi. Assume on contrary and take and take some point in the intersection. So this means that x belongs to En for all n greater or equal to 1. So which means that, but x belongs to En means that phi n of x is greater or equal to epsilon for all n greater or equal to 1. So this means the limit. What's the limit? What's the limit? Limit of phi n of x is greater or equal to epsilon. But what's the limit of phi? That's 0. This means that 0 is greater or equal to epsilon. But which is a contradiction because epsilon is a positive. A contradiction. A contradiction. As epsilon is a positive number. But here epsilon is less or equal to 0. So that means this intersection must be equal to phi. So thus intersection of En is n runs from 1 to infinity is the empty set, and hence we conclude that this En decreases to phi. And this En decreases to phi means that the outer measure will decrease to 0. Outer measure of En will decrease to the outer measure of phi, but outer measure of phi is equal to 0. It's 0. Now epsilon is already chosen. This limit is 0. This limit is 0. We can choose k greater or equal to 1 such that mu star of En minus 0, I can say the limit is actually 0, where minus 0 will be less than epsilon for all n greater or equal to k, because the limit of this mu star of En, its limit is 0. So it's a positive sequence and the limit is 0. So it means that mu star of En minus 0, then mod is less than epsilon. But we don't need to take the mod because mu star of En is positive for each n. So without mod, so mu star of En will be less than epsilon for all n greater or equal to k. So in other, this means in particular this is true for k also. So mu star of Ek is less than epsilon. So also this phi k of x will be less than epsilon for all x belongs to the set which is not belongs to B minus Ek, where B is the set where phi k of x is positive. So x is not in Bk, it means that phi k of x must be less than. Let's see the definition of Ek actually. What's the definition of Ek? So Ek is Ek, definition of Ek. You can see the definition of Ek here. What's Ek? Ek is the x belongs to x such that phi k of x is greater or equal to epsilon. So it means that when x is not in Ek, then phi k of x must be less than epsilon. Okay. So here this x is in B minus Ek. It's not in Ek. It means that phi k of x must be less than epsilon. Also this phi 1 of x is less or equal to m, because m is the maximum of phi 1 of x. So which means that because since phi 1 of x is the greatest of each phi, greatest value of the phi is, because phi is decreasing sequence. So that means phi n of x will also be less or equal to m for all n greater or equal to 1, as phi 2 of x less or equal to phi 1, phi 3 of x less or equal to phi, because phi is a decreasing sequence. So phi of x less or equal to m for all n greater or equal to 1. Now let's see this. Let's see this. Now we see that. This one 0, which less or equal to phi n. The positive values will choose 0 less or equal to phi n. For x is in B, for x in B minus Ek, so phi n is greater or equal to 0, because 0 less or equal to phi n. Okay, 0 is less or equal to 5. Phi is the decreasing sequence, and 0 less or equal to phi n, 0 less or equal to phi n.